I want to continue on these same lines and continue to do some algebra with you. We just talked about how to find that crazy curve. The question would be, now that you have that curve, what can you do with it? Also, we go back, and one of the things we teach in our college algebra is how to find the slope of a line. You know, why do I need to know how to do that? I mean, it's a nice exercise. I'll pass the test, whatever it is. But there's actually a nice application for slope, and I want to show you that, and then kind of lead you into where the things you can do with slope, with algebra and calculating slope, and the things you can't do. Okay, so let's look at the same situation. I'm looking at the same kind of model that I've talked about. But before I get to the curve, let's talk about how I would calculate the average speed during stages of the trip. And really, I guess I would just look at, well, what was my average speed during the trip? Okay. Well, I can look at the distance and the rate and the time. The relationship between those three is distance equals rate times time. Dirt, that's how I remember it, D equals RT. But if you solve for rate, rate is distance over time. Okay? Well, the distance traveled here was 35.9 miles. The time it took was 42 minutes. So I've gone that many miles in that many minutes, and I'd really probably rather know miles per hour. So we do a little conversion. We talked about how to do these conversions. Multiplying by 1 so that the minutes cancel, and that works out to 51.3 miles per hour. Now, what does that have to do with slope? Well, if I asked you the question in a different way, if I said find, and I should mention what slope is. It's rise over run, change in y over change in x. If I were to say to you, okay, find the slope of the line through the beginning point and the end point, that would be the y 35.9 minus 0, and then the x 42 minus 0. And that works out to be the fraction there if you want to look at it. And it's still miles over minutes, which you can convert. But the point is that that slope is exactly the same as that average speed. And so if we have some way of describing, if we have points that relate time to distance traveled, there's no difference at all between the slope between 2 points and the average speed that we traveled between those 2 points. So that's a good trick for us. That's an application of slope. Now what I'd like to do is be a little more general and say, well, yeah, that's great for the points I collected, but what about the intervals somewhere in between there? I mean, how fast was I going on the interstate? That'd be a good question to ask. What was my average speed before I left Glasgow? These kind of things. Well, to get that, you've got to have that curve between the points. And we've talked about how to do that. What you have to do is you have to get a continuous model of the situation. And I'm going to do, this is actually the same problem we worked previous, where we got the Lagrange polynomials for each of these points, added them up. I'm going to do one thing. Since I want my answers in miles per hour, I'm going to convert these points. I'm going to change the times, which are currently in minutes, to the times in hours. It's an easy thing to do. You divide by 60 each time. And then also when I ask the questions, if the interval I want the average rate over is in minutes, I have to convert those to hours as well. So you get the Lagrange polynomials for each of these 5 points. You take 0 the first one, 2.5 that one, blah, 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 blah. Multiply it out and you get this formula, which I'll go ahead and flash up here and show you what it looks like. It does hit each of those points exactly, and it gives me a nice smooth curve through there. Okay? Now, what if I want to know my average speed during this interval of the trip, between 30 minutes in the trip and 42 minutes into the trip? Okay? Or if it were a certain leg of the journey, I just have to look back and estimate, okay, when did I get on the interstate and when did I get off the interstate? You know, that kind of thing. Okay? Well, what you do is you find the slope of the line through those 2 points on your continuous now curve, on that polynomial curve that we just graphed. Okay? So I take the 40 minutes and I convert that into an hour. That's actually 2/3 of an hour. Plug that into y, I'll get that answer, and then 30 minutes, I have to convert that into an hour, so that's half an hour, right? 30 divided by 60. But you take these, this gives me then the change in y. Be consistent with these numbers and get the change in x. This one comes first, so it needs to come first down here. And what I would suggest you do, actually, if you have a graphing calculator, is just get that in your graphing calculator and then use that to evaluate their function values. That's tedious, raising those things to powers. And it works out to be 33 and about 1/3 miles per hour. And what that is, here's a half. Okay, there's 1 point right there. 2/3 would be 6.6, so that's somewhere right in there. And so this miles per hour represents the slope, if you will, of that line through the 2 points. Okay? Now, if I wanted to shorten that interval, how fast was I going? I got a ticket 30 minutes into the trip. How fast was I going between 30 and 30? It was somewhere between 30 and 31 minutes into the trip. How fast was I going? What was my average speed during that time? Well, it's the same calculation. You take 31/60ths. You have to convert that into hours now. Put it into your formula, minus 30/60ths into your formula, and then divide by the change in those t values. And then again, I'm just using my calculator to get these messy numbers. That works out to be about 50.5 miles per hour. Okay, and again, you can see the slope. Here's the line that I found the slope of up here. There's half, and then the other one would have been somewhere right through there. And that's the slope through those two lines. That's the line through those 2 points, and we've calculated then the slope of that line. So it's a nice use for slope. Now, here's one that I can't solve very well, and this is really one we worry about the most. This is going to illustrate one of the weaknesses of algebra. What we'd really like to know is, what was our speed 30 minutes into the trip? You know, at a point, how fast was I going right then? You know, when I got the ticket, how fast was I going? Well, you can try that. If you plug that in, you're plugging in 1/2 and minus y at 1/2, and then 1/2 minus 1/2. And that's trouble. That's where things fall apart. Because what I have here is a 0 on the top and a 0 on the bottom. You know from probably repeated attempts to do so that dividing by 0 is bad, doesn't give you an answer. And so we don't know what that is. I have actually drawn the line. You can find that line, and you can find the slope of that line, which would tell you your instantaneous rate of speed. But to do that, you have to use a trick from calculus. Algebra won't pull it off because we're dividing by 0. In calculus, you learn this little trick for dancing around the 0 business in the denominator. In fact, you almost work out a way to where you kind of work out the 0 in the top and the bottom, you get rid of them, and then you can get the answer. So to answer tough questions like that, you got to keep going. Go ahead, and my advice is you find the nearest calculus teacher and ask them about derivatives, and they'll tell you how to do that. I'll flash up the work that I did there in a summary, and then we'll come back and wrap things up.